Okay, in this video I'm going to provide a demonstration of Bayesian SEM and AMOS where we are essentially testing a path analysis model. One thing that I want to mention is that when you are running path analysis through standard maximum likelihood estimation, which is the default approach in AMOS, you're not able to perform bootstrapping. And the unfortunate thing is that bootstrapping is the only approach that's available through the standard AMOS options that will allow you to generate standard errors and confidence intervals associated with indirect effects within your model. So it makes it essentially it's impossible through the standard route to test the indirect effects that you compute based on your sample data if you have missing data. So if you don't have missing data, then there's no problem. But if you do, then there's going to be a problem. So the Bayesian estimation approach using AMOS can be one way of dealing with that particular problem. So that's what I'm going to demonstrate in this particular video. So I have basically a path analysis model that's laid out, and I'm going to go under analysis properties right here, and we'll start off. I'm just going to click off of this, and I'm going to click on, let's see, for output, I'm going to click on indirect, direct, and total effects. And we won't do anything on Bootstrap just yet, but I'm just going to run the analysis this way. So when I run the analysis this way, you're going to notice that it says, I get an error that says, in order to analyze data with missing observations, you have to explicitly estimate the means and intercepts. So right there, you know that if you have missing data, you have to click on this. There's no other way to deal with that particular problem. So once I've clicked on that, I can click, and now I've run the model. And so if I go under estimates, you can see I get my regression coefficients and so forth. And under matrices, I get my direct, indirect, and total effects. So these are all the, I have the unstandardized and standardized indirect effects being represented here. So that's all good. But if I want to test those for statistical significance, if I had complete data, then I could go under Bootstrap, and I could, perform a bootstrap. I'll go ahead and add up, I'll do 2,000 samples and bias corrected confidence interval. So I could click on that. Now the problem is that when I do this, I get an error message, and it says a bootstrap cannot be performed when missing data. So there's our problem. If I want to actually test the indirect effects that I've just computed, I can't do that using the bootstrapping facility in AMOS. So that is a little bit frustrating, and so there's not really much of a workaround for that particular problem. One potential option is to essentially go through an imputation route, maybe create a data set and with imputed values, and then run the analysis. Another option is to essentially utilize maybe something along the lines of Bayesian estimation. So that's what we're going to do. So to perform the Bayesian analysis, what we're going to do is, first off, under analysis properties, I do have to click off of this. I need to click off of this and this. I'm going to leave these things as they are. So I have the indirect, direct, and total effects. I've actually asked for standardized estimates, squared multiple correlations, and so forth. The main thing, though, is that when you are running Bayesian analysis, you have to click on estimate means and intercepts. So it's not going to work if you try to run your analysis without it. Just to show you what I mean, I'll just click off of that. And down here we have Bayesian. I can click on that icon, or I can click up here on Bayesian estimation. Either works. But notice that it says that to do this, we've got to click on means and intercepts. So again, we have to do that. So I'm going to click on estimate means and intercepts, and I'm just going to go and save this too. And now I'm ready to go. So I'm going to go to Analyze Bayesian Estimation, and there you go. So now you can see we have a little unhappy face changing to a happy face. This right here is essentially reflecting whether or not we have convergence for our parameters in our model. So what we're trying to do is to make sure that we have stability in our parameters. So, basically what's going on, you also notice that the values within our tables are changing, and that's because the estimation approach involves taking simulated samples. So you can see this number right here. We have a 500, which is the burn-in number of burn-in samples, and then we have this right here reflecting the number of new samples that are taking place. And once our little face has changed from sad to happy, and essentially that's going to correspond with a convergent statistic value that's less than 1.002. Once that's occurred, we can basically stop the resampling and now interpret our results. So just to show you again, if I reset this so you can see what happens, we're starting at 500 burn-in samples, and these are new samples generated. It's unhappy moving to happy, and so at this point we can click on our little pause icon to stop this. Otherwise, it will just go on and on forever. So at any rate, first off, let me just note that if we want to evaluate the overall model fit, we can click on this button right here for fit measures, and you can see that we're generating a fit summary. And there you go. And so you can see that we get a couple of indices here. We have the posterior predictive p. Basically, values around 0.5 would be considered excellent fit. And so values that are really deviating from that more substantially would be an indication of poor fit. So so at any rate, it looks like our model is demonstrating a good fit. This is right here, this is the deviance information criterion. It's not really useful for evaluating the fit of a single model like this is. Rather, this is more useful for making comparisons between models. So if I was to run a different model with an alternate specification, then I could compare the deviance information criterion from those two models, and then I would pick the model with the lower value as the preferred model. So other things to note as you're looking at this, we also have we can also look at the posterior distributions for each of our parameters within the model. So you can see right here, I'm going to click on this button, and this gives me, this says posterior, and if I click on a given parameter, this is basically the posterior distribution for the regression slope for performance goals in relation to anxiety. And you can see it appears fairly normally distributed, or actually very normally distributed. And you'll notice too that we have the mean right here. This is the average of the parameter estimate across all of those resampling. So that's but it's very close to 0. And then we also have the standard deviation right here for those resamplings. So you can see that you see right here it's the mean and also the standard deviation. So the standard deviation is analogous to the standard error when you're running your analysis using maximum likelihood estimation. And you'll also note that we have a convergent statistic that's actually associated with each of the individual parameters within the model. This is really kind of reflecting the overall convergence right here. You'll also notice that we have a credibility interval. So you can see it's basically a 95% credibility interval that is appearing right there. So a credibility interval is just interpreted as the probability that population parameter would lie within a particular interval. Now, it's possible to perform essentially null hypothesis testing using credibility intervals. Just keep in mind that if the null hypothesis falls within a credibility interval, then we would interpret it as being one of a range of possible credible values that the population parameter may take on. So there's a bit of a difference in the interpretation of credibility interval as contrasted with a confidence interval that we're oftentimes used to using more of a frequentist paradigm. So at any rate, kind of looking right here, you can see that let's say our null hypothesis is that the population regression slopes are 0. Then you can see that 0 falls between the lower and the upper bound for this credibility interval. It actually falls outside of this bound right here for the relationship between mastery and anxiety. So we have a negative relationship right here. So you might say that this coefficient would be, or this effect would be deemed as significant. You also have another coefficient right here for anxiety to achieve, and you can see that 0 falls between the lower and the upper bound, so that would be perhaps deemed non-significant. So at any rate, those are some things to kind of keep in mind. Now, I mentioned about the indirect effects. So we can also get information on those. We already requested it through our analysis properties approach. But if I click on this button right here, I get additional estimands. And these are them. So I can actually kind of bring this down right here, and you can see the indirect effects that are shown up here. So these are the unstandardized indirect effects. You've got mastery on achievement, interest on mastery to interest, and so forth. So these are, this is, as you can see right here, it says indirect effects and it says mean. Again, that is the average of the indirect effects for the posterior distribution for the indirect effects. The standardized indirect effects, this is it right here. If you want to get the lower bound for the interval, credibility interval, you can click on this button right here. So it says 95% lower bound, and then there's the upper bound right there. So you can click between the lower and the upper bound, and so then you can still theoretically use that null of 0 to test out those indirect effects. So at any rate, you can see that that you can basically do a lot of the same things that we were doing before with respect. When basically we can test out those indirect effects in the context of our path analysis when we have missing data, just using the Bayesian approach as opposed to the attempting it with maximum likelihood estimation and getting those error messages.